Just jump right into it, part three. Okay, so we're gonna talk more about limits, but limits as x approaches infinity, or what if the limit itself is approaching infinity or negative infinity, right? So if we look at limits involving infinity as x approaches plus or minus infinity, um, so if you think about it, you're looking at the far left or the far right. Clearly, if you're going towards negative infinity for x, that's far left. If you're going to the positive for x, that's far right. So and obviously, we're going to look at numerically what's happening graphically and analytically. We're going to look at all three of those again. So let's start with example one. This one's pretty obvious. It should be pretty easy to understand. That's y equals 3, right? So it's pretty clear. You have a flat line. So what will be the limit as x approaches negative infinity?
3.
How about positive infinity?
3.
There you go. So if you ever have the limit of a constant, it's just going to be the value of the constant itself. And there actually is a horizontal asymptote, believe it or not. It's actually y equals k. I know it's kind of weird. Yeah, exactly. It's all about end behavior. So the one misconception, which I want to clear up, I don't think you guys have this issue, but I tend to have with like regular maths, like regular pre-calculus students or regular algebra students. The horizontal asymptote is not a boundary graph can't cross. In fact, it can cross it or even coincide with it, like in this case here. Far left, the far right. Yeah, so you could totally cross horizontal asymptotes or coincide with them.
Just like what value it approaches.
If it's piecewise, you can. You could put a dot there. If it's piecewise, you could do that. But as a general rational function, no, you don't, right? Because it says it's continuity clearly. But for any other function like exponential or rational functions, things like that, the horizontal asymptote or a logistic, that's another one we've seen too, horizontal asymptotes. It's all about approach, but also the far left and far right. So as x is going towards infinity or negative infinity, what is y doing? What are the ends of the graph doing? How are they behaving? So does it look linear? Great. Does it look horizontal? Great. Whatever it is, how's it looking? Sometimes it could be oblique, like meaning it could look like a parabola. It could, depending on the long division or the, whatever division you have to do between polynomials to see what behavior it has. That's why we do like all that division stuff. So a lot of that polynomial division is going to be coming back in this topic here because we have to see what the graph is doing on the far left and far right. So that's all it ever is, just so you know. So don't think it's, oh, I can't cross it. No, you totally could cross it. It's not a problem. Maybe sometimes it can look like a boundary, like in the case of example 2, but not all the time. Okay, so let me just kind of push this over here. All right, so next up, 1 over x. You guys should know what's happening with that one. That looks like this here. And I'm just going to kind of do that there. So it's going to be 0 in each case, right? And you do have two asymptotes. You have a horizontal and a vertical. We'll look at the vertical a little later today. Does that make sense?
Mm-hmm.
Okay. Cool. And the equation of asymptotes is pretty simple. Just y equals 0. And yeah, just 0 in each case. And even if you have a constant greater than 0 for n, it's still gonna be 0. There's not really any analytical work here. That seems kind of not really much work to show, I'd say. Really just think about it as you do one over a large number.
Yeah, I think
That's just zero, right? Roughly zero. Like we know that. So I don't think we need to really think too hard about that one. So we're okay? Makes sense? Okay. Um, okay, we're good? All right, let's move forward. Um, okay, let's keep moving. Okay, so in general, this is really how a horizontal asymptote is defined as from a limit perspective, right? This is why we spent all this time about rational functions earlier in this semester. Oh, do you need notes, guys? Oh, okay, I didn't see it. Okay, I couldn't see it. So yeah, y equals b will be horizontal asymptote when this happens. And it doesn't have to be both. It could be one or the other. For example, when we have a logistic function, they look like this, right? It had two horizontal asymptotes, right? Remember two? So in order to be defined as a horizontal asymptote, you need the limit as x approaches infinity equal a finite number. Okay, let me actually write that down for you guys. From a calculus perspective, a horizontal asymptote arises when the limit as x approaches positive or negative infinity, or both, approaches a finite value. That's really what a horizontal asymptote ever is. From a limit or calculus perspective, arises when the limit as x approaches positive or negative infinity for x, the limit itself approaches a finite value. So that's all it ever is. So let's take a look at, let me push this off to the side here. Okay, so let's look at sine x over x. If you were to graph that, I think it looks, there's a hole here, I believe. It's going to look like this, kind of like a snake. Okay. We'll use a table to work this out in just a moment. But I'm going to tell you right now, in both cases, the answer is going to be 0. So it actually does have a horizontal asymptote. Believe it or not, it does. It's y equals 0. And actually, I'll use my calculator. I'm not going to display the calculator because I just don't really have space to do so. But if I go to y equals, oh, geez. Okay. Sine x over x. And by the way, I gotta be in radian mode. Very important. Gotta be in radian mode. So sine x over x. Let's see here. Sine x over x. We go to alpha trace, y1. Let's plug in 100. Let's plug in 1000. Let's plug in 10,000. You should get this. Negative 0.005. 8.269 times 10 to negative 4. Negative 3.056 times 10 to negative 5. Okay, hopefully you guys can read that. I'm sorry if you can't. let me write better. My apologies. The first was negative 0.005. Next was 8.269 times 10 to negative 4 scientific notation. And 1,000 will be this. Sorry, 10,000 will be this. Negative 3.056.
It's the same for the.
I don't know. We'll see. Yeah, actually it is. Yep. Okay. So even though it's crossing the x-axis infinite times, right? It's not a boundary, it's about approach. What's y getting closer and closer to as x approaches positive infinity? It's getting closer to a finite number. Is it going to be exactly? No. Actually, sometimes it can be. But is it gonna cross many times? Yes, it is. So again, it crosses many times, and that's okay, because that's not the true definition of it. The true definition is about approach. So it doesn't settle on zero. Put it that way. That's what I was trying to say. So it's going to be so if you get this, sorry, you would get this in each case. You get that would be zero. That would also be zero, by the way. And you can use this even for more complex problems. We can take advantage of that that concept. So questions? All right. Before we do example 4, before we do the table, do you guys have a general idea what these limits would be for that one? For 2x or root x squared plus 1? What do you guys think that's going to be? You're going to take a stab? Was that? Not 0. Why 2?
Because x squared plus 1, as it gets really large, it's basically just going to be x.
Yeah. Well, what if I plug in 100? What's 100 squared? 10,000, right? But then you add 1. But isn't the square of 10,001 pretty close to the square of 10,000? And square of 10,000 is 100. So it kind of gets back to where it was before, right? And you have 2x. If I plug in 100, of course I get 200. What's 200 over 100 or close to 100? 2. Yeah. Yeah. So we call this end behavior models. We'll talk about that in a moment. But yeah, it's gonna be 2 in each case. I mean, I'll plug in just to prove to you. So let me go type this in. 2x divided by parentheses. I don't need a parentheses. Oh, yeah, hold on. 2x in parentheses divided by root x squared plus 1. Alpha trace y1 100 10,000. Yeah, it's basically 1.999. I mean, I could write a whole bunch of 9s if you want me to. And if I plug in negative values, oh, this is interesting. It's gonna be negative. Oh, yeah, that's really interesting. This says 2. Yeah, sorry guys, I messed up. That's supposed to be negative 2. So it's 2. Yeah, because remember we talked about square root of squares? Because this is approximately an approximation could be thought as like this: 2x over absolute value of x. Think about it, right? If x gets large, that plus 1 becomes negligible, right? That plus 1 doesn't matter anymore as x gets large. And so if you think about it, that's totally going to be 2 different values as x gets really big. Either 2 or negative 2. Because remember we saw this earlier? Remember that was a piecewise function, it was 1 and negative 1. Now you just put a 2 in front of it. That's what's happening. So to analytically determine it, I'll do it down below. Yeah, let me actually we don't really have, well, like a little bit of space, I suppose. Actually, I kind of did it. I'll just do it again down below.
Wait, didn't we already do this? Very good.
Yeah, analytically determinate. We call this an end behavior model. So I did say we're going to talk about that. When we do the end behavior model, focus on just the leading term. For both numerator and denominator. Okay. So in this case, y will equal, what's my leading term above? Just 2x, right? And that's square of x squared. So you ignore the plus 1. Ignore the plus 1 there. And that became what again? 2x over. And you can write a piecewise function like this. 2 and -2. This is if x is bigger than 0 or if x is less than 0. And that's what you do. So that's how you, and then when you evaluate the right limit, it's 2, the left limit is -2, or positive infinity, negative infinity. So does that make sense? How you broke that down?
You would rather us write it like an absolute value than like.
Yes,
like,
100%.
What would you?
Well,
rather?
well,
I mean, it's the same
this,
thing.
and then just show this, how this breaks down this way. Questions over, yes, go.
Square root of square, it's basically the same as that.
Yes, exactly, right, because we said like it has to be a positive outcome or output. But the plus 1 gets ignored because what's x approaching? Infinity, right? So we ignore it. You ignore it because yep. You ignore it, you ignore the plus 1 because it's insignificant. I can't write anymore. It's insignificant when x is large. Sorry, I just can't write anymore, but that's why we ignore it. And that's called an end behavior model because you're looking at, it's forced you to look at the ends of the graph, like what really matters. The ones the highest degree because they have the most impact on the function. And but for both. Yeah. So like, for example, when we have rational functions, which we'll talk about next page, we have to focus on that.
Wouldn't it be like leading term and like exponents?
The same thing. The leading term is the one that has the highest exponent.
Oh, okay. Oh,
That's what I mean.
leading.
For both. The highest exponent for both.
Nothing else matters.
Yes, exactly. Nothing else matters. Right. Correct. So actually, with that thought in mind, let's jump to example 6. And I'll come back and do example 5 in the table up above. But let's jump to example 6 with that in mind. So if you think about it, it's really like saying this. What does that reduce to? So it's just 2/3, right? Now, there is, so this right here, this process is a quick and easy way. There is a more formal way, which I do have to show you, which is a little bit of a pain, but I have to show it to you guys. So that process I just did, just focus on the leading terms, is a quick and easy way. But the more formal way is this. The limit as x approaches, and I'm just going to kind of consolidate all of it. I'm not going to do this twice because that's kind of stupid. I'm just going to consolidate like this. So far, would you agree that everything I'm doing seems valid?
Mhm.
Because I'm doing the same treatment, both top and bottom. Like if I have a fraction like 4/5, multiply top and bottom by 2 and 2, I get 8/10. Same thing, right? Doesn't really matter. By doing this, what do I accomplish? What cancels?
50.
Yep. So now you get this. Limit x approaches plus or minus infinity. What does the top become now?
2
What does the bottom become?
b minus 2 over x squared.
Correct. Now, if I think about it, if I evaluate it, that's how you can express this answer. Because then we say 2 over x is 0, or any exponent that's positive,
Oh, yeah.
right? Because who cares what that exponent is? If x is getting large, how does that 2 compare to a large number as x approaches positive or negative infinity?
Sure.
It's negligible, right? Even if it was just plain old x and you have 2 over a negative number, that's still getting close to 0, right? Because that 2 is static. That's dynamic. That's moving fast, big. So that goes towards 0, and these are static also, 2 over 3. That's why you get that. That's really good.
Why is it that when you have like, say like an x squared over x cubed and like approaching,
Mhm.
why do you do like the ratio of the exponents? Like when you're finding,
You don't do the ratio of x, you do the ratio of the powers, x squared over
Uh.
x cubed, which is 1 over x. And then that just goes towards 0 as x approaches infinity. That's all.
Okay.
Yeah, it's just when you have x cubed, that increases more quickly than x squared ever would.
yeah.
So they start to diverge. So they're pulling away from each other.
Let's say like,
And because the bottom's
with, like,
higher
number 6,
degree.
I think I'm trying to ask something else. Like with number 6 in the homework.
Mhm.
Like as I was solved, so you get like 2/3, I think was the answer.
Well, that was a little different. That was
Yeah,
that was the things
this was
factor. That
different,
was
yeah.
different.
Um,
That did I approach infinity?
no.
Okay.
It was as it approached 0.
Right,
so-
correct. Yes, right.
So why was it? So
Because
what I did was-
that's not end behavior. That's x is approaching a finite number.
Okay.
That's way different. Yeah, we're only talking about x approaching infinity right now. That's it. The far left and far right. But we'll definitely talk about the homework in a little bit. The next homework. But yeah, you just get 2/3. That's all. So that's why we can generalize with the ratios, right? Like if the degrees are the same, you could say it's just a over b, or the ratio of the leading coefficients. That's why we can do that. Before I talk about the generalization, let's actually, there should be something on that. No, well, it's interesting. Okay, well, whatever. But let's come back to at the top of the page now. So yeah, even if x is approaching positive or negative infinity, it doesn't really matter. The limit properties still apply. You can still use the same limit properties. Let's say you have fx and g of x are 2 separate functions. And each of those limits are unique. L and M is for f and g respectively. X approaching positive infinity or even negative infinity for that matter. You can still use the limit properties. It's all the same. Like if we have sine squared x, if you think about it, wait, sine squared x, that's weird. Well, hold on a sec. Would that even exist? Oh, yeah. So in this case, well, I'm a little confused now. What do they want for that one? Okay, this is where I pull up my notes now, 'cause I'm a little... Oh, I see. Got it. Okay. I think I see what's going on here. Actually, do I see what's going on? Give me a sec.
Graph it.
Yeah, it just seems weird to me. But I just wonder why that was asked. That just seems kind of random. Okay. I'm just trying to understand the intent of it, like how it ties to the limit properties. Yeah. Anyway, yeah, just graph it. That's pretty simple. Yeah, kind of like a snake, right? By the way, it's never negative because you're squaring sine, right? So it'll be D and E for both. So there is none. Yeah, I'm just trying to understand what was the point of that question. But it makes sense if you look graphically, because can we ever settle? Not settle, but does it get closer? No, it doesn't approach, right? It's kind of like oscillating in a way if you think about it. It's going back and forth. Yeah, it's never getting closer to a certain number. It's just between 0 and 1 the whole time. Correct, right. Likewise cosine x. Right. Okay, I think that was all that was happening there for that one. All right. Let's keep moving.
Tangent X just have like infinite.
That's a vertical asymptotes or infinite continuities. We're gonna get there. Yeah. Okay, let's do another one here. So I want you guys to do, and we'll just consolidate this again. So let's write it like this. The limit as x approaches plus or negative infinity.
So like off initially seeing this one, like, and I get a guess be that it's 2/3.
No, it's gonna be it's not gonna exist.
Sorry. Oh, so you only look at one. Oh, I see. But you always just do this to get rid of the.
Yeah, what you do is you choose for the formal, right, for the formal method of showing
How do you know?
this limit analytically.
Yeah.
Choose the reciprocal of the highest power for both. Yeah, so what you want to do for the formal method of showing this limit analytically, you have to pick the highest power among both. So what's the highest power among both of these? X4, right? So I'm doing the reciprocal of that. 1 over X4. Now, if I do that, what does the top become?
2 minus 7 over x².
Correct, right? So you have 2 minus 7. I'm making it that way. I'm just consolidating it. I don't want to do this limit twice. I don't feel like it. Oh, like square of x squared. Yeah, well, in that case you should. But like I just for the sake of like saving time, I know rational functions only have one horizontal asymptote. Well, when we had the one that we just did with the square of x squared plus 1, that's not a rational function because you don't have a polynomial in the block, right? Here I have 2 polynomials, so I know it's only have one horizontal asymptote or none. In this case, it'll be none. So I get 3 over x cubed plus 5 over x to the 4th. So if I think about it, I have 2 minus 0. So in this case, it does not exist. And in fact, actually, it's positive infinity. Dini's fine. Dini's fine. Yep.
So that's. It's not a fraction, it's like.
Right. So why don't you guys try example 8? Just do the same process. I think we know what the answer is, but do the same process for example 8. And I'll do it as well. We'll check our work in just a moment. Correct. Oh, actually, this is gonna be y equals 0. Yeah, we know what this is. Yep.
What? Wow, okay, the bottom's right.
Yep.
So we should.
You can do 1 over x4 again.
We're not doing this one.
No, we are doing. Yeah, I'm doing it on my own. You guys do it on your own.
Close the answer.
I know. It's just more just writing it out. Okay, so your answer should look like this. If you do it formally, choose the highest power among all the terms, both top and bottom, which is x4. Do the reciprocal of 1 over x4. Multiply top and bottom by it, clean it up, you should get 3 over x, let's say over x squared, the x cubed. 5 minus 1 over x cubed. Each of these fractions go towards 0 when x approaches infinity. 0, 0, 0. So 0 plus 0, 5 minus 0 is 0. So it's 0. And of course, that's a horizontal asymptotes. That's what we're seeing.
Can't you also just like tell it with like the rule, like the highest degree? Or is this
Yes.
just showing
This is
analytically?
just showing analytically. That's all I'm doing. Yeah. It's just the formality of it. Remember, I'm teaching as like an AP class now. That's all. Yeah. Does that make sense? We're okay with that? Okay. Just trying to think my pacing here. Okay. Let's keep moving. Oh, we got what time? At 11:15. Okay. Oh, we got a long lunch today. That's lovely. All right.
We have a long lunch.
Yeah, 50 minutes.
I want to know.
40.
Really?
Tomorrow's short. Tomorrow's only a half hour.
Why?
Because
How comes that?
we have mass.
Is it formal dress?
Yeah.
I didn't see any of it.
Ross formal dress?
Yes, it is. We were a Catholic school. Of course you have to dress.
Oh, yeah, but that was
I
something.
didn't send out a.
Ah,
Well, now you do.
Then.
Now I know. All right. So for part A,
They didn't say.
I'm just gonna give you kind of the answers.
that's the tire required. Oh.
Actually, I'll just kind of write it over here.
That's so rad. Where is Bennington? We need a little bit of VT, was VT Virginia Tech in Vermont.
Okay, let's work these out. Okay, e to the x looks like this. E to negative x looks like this. And 1/2 to the x looks like this. So that's why we spent all this time learning how these graphs look for this moment here. What do you think about for a growth function, exponential growth function? If x approaching negative infinity, what's y approaching? 0. But if x approaching positive infinity, what's y approaching? Positive infinity. Or you could say D and E, either one. Okay, for decay, if going further to the left, what's y approaching? Positive infinity or D and E. Because what's infinity? I don't know. There's no limit. Sky's the limit. It just goes up forever. Right? Or if it's x approaching infinity, it's gonna be 0 for decay. And you'll see the same thing over here as well. Because 1/2 to x is decay as well. All's good? Yeah. All right.
Does it matter like if we continue here?
I don't care. I don't care.
So is this one where we should, this next one, should we just do the whole like properties thing?
Yeah, exactly right. So what I'll do. So again, that just think about it numerically, exponential growth function, think graphical what's happening, visualize it. There's really nothing analytical to do for example 9. It's more numerical, as I said, so or even graphical. You can think of it that way as well. So we could just kind of just state it. Let me freeze the screen while you guys are still copying. So let's look at example 10. Example 10, I'm gonna write this out and show it to you guys in moments. That's how you show it, guys. If you have two separate expressions, actually, you can break it down to
I guess we're moving.
like 5 or 6 separate expressions if you wanted to, but if we just separate the two sets of parentheses, like, hey, let's find a limit in the first group, find a limit in the second group. Okay, this one, and you use the limit property, right? You know, you can times them, because they're each gonna have their own unique limits, that's fine. That's 7 minus 0. The other one is 0 plus 3. Because e to the negative x is decay. 7 times 3 is 21. So, don't overthink it again. They're really straightforward. Okay, last one of these before we talk about vertical asymptotes. I'm not gonna do squeeze theorem today. We won't do that today. I'll leave that out. So once I get through example 13, then we'll stop our notes for today. Okay, questions so far? No? Okay, let's keep moving. All right, here's what I'm gonna do for this one. Write this as a piecewise function. So you can write like this.
Some weird shit.
Okay, in case you guys are still struggling with how to rewrite this as a piecewise function. So absolute value breaking out into two things, right? As we should. Absolute value will equal itself. If the inside stays positive. Or the absolute value would be the negative counterpart of what's inside. If I change the x values to make it negative. So for example, what would guarantee a positive output for x plus 5 when x is larger than negative 5? Like negative 4.999 or negative, or sorry, or like 20 or a million or whatever, right? Whatever it is. If I do that, then yeah, of course, that's gonna stay positive. So great. So just leave it alone. What if x is negative? Sorry, what if the inside is negative? So what makes the inside negative when x is less than negative 5, like negative 6 or negative 5.01 or negative a million, whatever, right? But how do I guarantee the same output or results? Leave that negative. Leave it plus negative. X plus 5. To do that. And then, of course, can I clean up a tab more? Sure. How do I clean up a tab more? What would I say? Yeah, exactly. Yeah, exactly. So this will be negative 5. Or hold on a sec, that all cancels. Or 2x plus 5, exactly right.
Right, so the top one, since you're multiplying it by -1,
Mhm.
you have to, like, the restriction on the x values are whatever values keep it negative,
Correct, right.
like produce a negative value.
Correct, right. So if I graph it, oh boy, I didn't really. Well, let me move that around. Yeah, so you can have that right? And then the other one, if I plug in, they do link up actually. And slope is 2. You agree with my graph? So what's my limit going to be? What's the value of my limit? -5, yeah. Based on my graph. So you rewrite, do a graph. Like, think about it. Like if x is negative 100, that's negative 100, but plus outside negative 95. What's outside negative 95? 95. What's negative 100 plus 95? Negative 5. Every single time we get negative 5s as a result. You good?
I don't
We good?
understand, what's wrong with my graph? I'm on
Everything.
no.
Well, dude, you didn't plug in negative. Well, no, you start at -3. Why you start at -3?
Dude,
You start at -3. Why? I don't know. You tell me.
where did I start? Where's -3?
That's -3.
This is with 2x plus 5.
Yeah, but
Your graph should be starting at -5.
This plus
But that means all.
x is less than.
Oh,
Oh,
exactly.
oh,
All right. Okay, let's see. I don't want to rush this, but let's see how I can do with this today. Okay, 1 over x again. We know what's happening here. You have all this junk, right? Okay, all's good. So if x is approaching 0 from the left side, it's negative infinity. 0 from the right side is positive infinity. When this happens, we say it's x equals 0. We'll say the limit does not exist. Okay, so we're okay with that so far? That all makes sense? Okay. So when this happens, when x is approaching a finite value, but the limit is positive or negative infinity, that gives rise to a vertical asymptote.
when x versus it. Oh, when there's like two different.
Right. So if we think about it, let me put the text box.
Oh, I like the superscript.
When x is approaching a finite value, but y approaches positive or negative infinity, then the graph has a vertical asymptote at that x value. Approaching a finite from either the left or right side of it. Okay, that's the true definition of a vertical asymptote. It comes back to limits again. And by the way, any one of these has to be true. You don't have to have all of them be true. If any one of these, at least one occurs. So as a piecewise function, you could have a approach, the graph approach positive negative infinity on the left side, but on the right side, like for example, I could have this. Or as a piecewise function, you totally could have this. This is a very possible. This still counts. I know it's weird, but this still counts. This still counts as vertical asymptote because it's all about limits. It's all about approach. If the left-hand limit, like, let's say I call this like 2, right? What's my left-hand limit here? Negative infinity. What's my right-hand limit? Some random number. You only need it to happen once, just once. Okay. So let's look at this from example 13. And once I get example 13 done, then we can be finished. All right. So let's look at example 13. Let me move this off to the side, this statement here. Okay, so I'm not sure how we would do this analytically necessarily. But what I do know, actually, I do know this analytically. I lied. Analytically, sign chart, guys. Remember sign charts? Oh yeah, they come back with a vengeance of calculus. So get used to them. All right. Let's do. Okay. Remember I talked about how an efficient way for doing sign charts? Focus on the far right interval. What's my far right interval? X is larger than what? 3, okay. So 4, for example. If I plug in 4, that first factor is positive or negative. Next one. Next one.
Positive.
What happens if you multiply and divide a bunch of positives?
Positive.
Positive. Good. Good. Okay. So I would be in agreement there. Now, every factor, are they all linear? They are. There's no square symbols. It's not x minus 2 square, x minus 3 square, whatever, or an absolute value or anything weird, or square roots. So we do expect an alternation of signs. You can test if you want. You want to plug in 2.5? Go ahead. You want to plug in between -3 and 2? Go ahead. Want to plug in number less than -3? Go ahead. But I trust that every factor is linear. We're going to have this alternation of signs. Okay. Now, because we're going to have, it's going to be undefined. Because undefined there, here's what's going to happen. I expect, I'm just going to kind of just write this out without really giving it much thought. Well, I am giving it thought. But I'm just going to kind of just write it and then we'll just think about it after that. Okay. Without actually plugging in negative 3.01 or negative 2.99 or plugging 2.999 or 3.001 or even graphing it that. The sign chart's good. Because think about it. I know if I plug in -3, it's going to bottom. And if I know plugging values close to -3, the bottom's just going to get tinier. But when you have a tiny denominator, overall the fraction gets bigger. But does it get bigger towards positive or towards negative? That's the question, right? Likewise, if I plug values close to 3, like say 3.01 or 2.999, the bottom gets smaller, but the bottom gets smaller, overall the fraction gets bigger or more negative. Well, think what's happening to left -3. What's happening to left -3 here?
Oh,
It's negative. So it has to be approaching negative infinity. What's happening to the right of -3? Positive. It's got to be approaching positive infinity. The same thing's happening to the left and right of +3 as well. So you don't necessarily have to do a graph. If you want to do a graph, go for it. I'll go Desmos really fast just to show you. Let's see here. Desmos. Y equals, what was it again? X minus 2. X squared. There you go. The graph shows it. Right? But you could get away with it without the plugin or do graphs if you just think about it from the sign chart perspective. The sign chart will help me tremendously there. And my asymptotes, again, I'm not gonna do squeeze theorem. I didn't plan on it anyway. I didn't want to. I'm sorry, dude. We'll do it tomorrow. Not tomorrow, Thursday. And good for you. Yes, these are some logic. Yeah. So that's what's happening there. So hopefully now we have a better understanding of limits from an infinite perspective, like x approaching infinity. It's like a horizontal asymptote, or if x approaching a number, but y is infinity, that's its vertical asymptote. That's kind of the key takeaway from today. And we'll kind of I'll keep being this into you guys as time passes. Really quickly, homework is going to look like this.
You get it, or is it like infinitely long?
Well, okay, why don't you guys negotiate this with me? I do want you guys doing 14, 15, 16, 17, because we didn't do that yet. And then for handout C, I want you guys doing about like 35 problems. I was joking. Okay. What should I say odds instead of all of them? Would that be fair? Or should I just pick maybe like every third problem? Are we multiples of 3? Because 21 problems, multiples of 3, we're okay with that? All right, okay, multiples of 3, help that. Okay. We'll do multiples of 3. Fair enough. So we'll do 3 through 21 every third problem on handout C. There are 2 handout C's. It'll be the first handout C we have, you guys, not the extended, the first one. Okay.
Damn, bro, how much homework were people doing in this class?
I don't know, man. All right. Okay, so then I'll see you guys on Thursday, right? Right. Enjoy your lunch. You guys can go. Yeah. Welcome.